Picture this. It's a Tuesday morning at a mid-sized engineering team. A developer pushes a commit at 9 a.m., sees the CI pipeline kick off, and knowing it'll take 45 minutes opens a new task. By 9:15, they're deep in a different problem, a different mental model, a different code base. Then at 9:47, a red notification lands in Slack. The pipeline failed. But by now 3 more pull requests have been opened on top of the broken commit. 2 of them are already approved and waiting to merge. The developer stares at the failure. They can't remember what they were thinking 2 hours ago when they wrote that code. Reconstructing the context takes 15 minutes. The fix takes 5. The debugging to find which of the 4 stacked PRs introduced the regression takes another 2 hours. This is not a hypothetical. It is Tuesday morning at thousands of engineering teams around the world. The pipeline takes 45 minutes, so nobody waits for it. Nobody waits for it, so nobody catches failures early. Failures compound on top of each other, buried under layers of new work. By the time the rot is found, it has become structural. Slow CI is not a minor inconvenience. It is a compounding tax on every engineer, every day. And the brutal irony is that the teams who need fast CI the most, the ones moving fastest, shipping most often, are precisely the ones who suffer the most when it's slow. This chapter is about what makes a CI pipeline great. Not just functional. Not just green. Great in the sense that it actively accelerates your team rather than slowing them down. Strip away all the tooling choices, all the YAML configuration, all the cloud runners and container registries and artifact caches, and what you're left with are 3 non-negotiable laws that every great CI pipeline must satisfy. Break any one of them and the pipeline begins to fail at its fundamental job, not catastrophically, not all at once, but slowly and invisibly. The first law is fast feedback. A result in under 10 minutes from the moment code is pushed. Not 15. Not 20. 10. Because 10 minutes is the boundary of focused human attention, the window in which a developer can still act on feedback without rebuilding their mental context from scratch. The second law is deterministic results. Push the same code twice, get the same result twice. Every time, without exception. This sounds obvious, but it is violated constantly by flaky tests, by pipelines that depend on network calls, by builds that embed timestamps, by tests that share mutable state. Determinism is the foundation of trust. And CI without trust is just decoration. The third law is blocking broken code. A failed pipeline must stop the merge. Not warn, not report, not suggest, stop. A CI pipeline that can be bypassed, that can be overridden by an impatient developer or an overly trusting reviewer, provides a false sense of safety that is arguably worse than no CI at all. These 3 laws are the lens through which everything else in this chapter should be understood. 10 minutes is not arbitrary. It was not chosen because it's a round number or because it fits neatly on a slide. The 10-minute threshold maps precisely to the outer boundary of focused human working memory, the cognitive window within which a developer can hold the full mental model of a change they just made and respond to feedback without having to rebuild that model from scratch. Jez Humble and David Farley articulated this clearly in Continuous Delivery back in 2010, and 15 years of industry practice have done nothing but confirm it. Under 10 minutes, a developer can reasonably wait. They might grab a coffee, review a comment, or look at a small related ticket, but they stay in the same mental workspace. When the result comes back, they act on it immediately. The cost of a failure is 1, maybe 2 minutes of fixed time. At 20 minutes, the situation changes meaningfully. The developer has started a new task. When the CI notification arrives, it is an interruption. They have to mentally stop what they're doing, context switch back to the original PR, reconstruct what they were thinking, understand the failure, and then switch back. That process costs 5 to 10 minutes of recovery time even before the actual fix. At 45 minutes, it's not an interruption anymore, it's a derailment. The developer is deep in a new problem with a completely different mental stack. The cost of switching back, as we'll see in a moment, averages 23 minutes of recovery. Multiple PRs may have stacked. The entire sprint trajectory may have shifted. What would have been a 2-minute fix when caught immediately becomes a 2-hour investigation when caught late. There's a particular kind of CI failure that is more dangerous than a broken test. More dangerous than a slow pipeline. More dangerous, even, than no CI at all. It's the flaky test, the test that fails on the same code, at random, for no apparent reason. Sometimes it passes. Sometimes it fails. Nobody can explain why, and nobody wants to spend 2 hours debugging a test that might just pass on the next run anyway. The immediate problem with flakiness is the false alarm. But the real danger is what it does to your team's behavior over time. The first time a flaky test fires, the developer investigates. The second time, they're a little less thorough. By the fifth time, they've learned a new habit. When CI goes red, the first assumption is that it's probably the flaky test. Rerun the pipeline. Don't investigate. Move on. This is what psychologists call learned helplessness, and it is catastrophic for the safety guarantee that CI is supposed to provide. Because now, when a real failure occurs, developers apply the same heuristic. Rerun. Probably just flaky. Move on. The real bug slips through to main, to staging, to production. And when the incident happens, everyone is shocked. The CI was green. Green means go is the entire value proposition of continuous integration. But that proposition only holds if green is perfectly trustworthy. A single flaky test in the blocking suite is enough to poison the entire pipeline's credibility. Determinism isn't a nice-to-have. It's the thing that makes everything else work. Let's be precise about what we mean when we say CI must block broken code. We don't mean that CI should report failures. We don't mean it should post a comment, or update a status badge, or send a Slack notification. We mean that the merge button must be physically unavailable until every required check passes. Not socially unavailable, physically unavailable. The distinction matters enormously in practice. A soft CI gate, one where the pipeline runs but merge is not blocked, creates a dangerous social dynamic. Developers who are under deadline pressure, who are confident their change is safe, who have seen the pipeline be wrong before, will merge anyway. They'll tell themselves it's probably fine. They'll tell reviewers it's a known flaky test. And usually they'll be right. Until the one time they're not. A hard gate removes that social pressure entirely. There's nothing to argue about. The button is gray. The code doesn't merge. Full stop. GitHub enforces this through branch protection rules. You require status checks to pass before merging and list the specific CI jobs that must succeed. You also require branches to be up to date, which prevents the common failure mode where a PR passes CI against a stale version of main but would fail against the current version. One more thing that teams consistently get wrong: repo admins bypassing their own rules. If administrators can override branch protection, you don't have a gate, you have a suggestion with extra steps. The rule must apply to everyone, including leadership, including the person who configured it. That's the only way the guarantee holds. In 2005, Gloria Mark, a researcher at the University of California, Irvine, published a study that changed how we think about workplace interruptions. She and her team shadowed information workers throughout their day, measuring not just how often they were interrupted, but how long it took them to return to their previous level of deep focus after each interruption. The number she found has haunted productivity research ever since: 23 minutes and 15 seconds. That's not the time to understand the interruption. That's not the time to handle it. That's the time after the interruption is resolved, after the developer has looked at the CI failure, understood it, and either fixed it or filed it before they are fully back in the deep focus state they were in before the ping arrived. Let's run the math on a 45-minute pipeline for a team of 10 developers. Assume the pipeline fails 3 times per day, a modest number for a team actively shipping. Each failure triggers a context switch costing 23 minutes of recovery. That's 69 minutes of lost deep focus time per developer per day just from CI interruptions. For 10 developers, that's over 11 hours per day, nearly a full engineering day, consumed by context switch recovery before a single line of productive code is written. Now flip it. Fix the pipeline to under 10 minutes. Developers wait for the result. There's no context switch. The failure costs 2 minutes of fixed time, not 23 minutes of recovery. That 11 hours per day comes back to your team. Every week. Every sprint. Every quarter. Fast CI is not just a developer experience improvement, it is a fundamental multiplier on engineering capacity. Google operates at a scale that makes most CI problems look trivial. Their internal monorepo, a single repository containing the code for virtually every Google product, has over 2 billion lines of code, is modified by tens of thousands of engineers, and generates more than 50,000 CI builds every single day. Understanding how they've structured CI at that scale is one of the most instructive case studies in software engineering. The core architectural decision Google made is the split between pre-submit and post-submit CI. Pre-submit runs before code lands on the main branch. It's a fast, curated subset of tests designed to catch the most likely failure modes in under 10 minutes. It is deliberately incomplete. Not every test suite runs. Not every integration scenario is covered. The goal is speed and actionability, catch the most common errors before they land. Post-submit runs after code is merged. It executes the full test suite, the full integration battery, the complete contract between every service. This is where thoroughness lives. If post-submit catches something, a revert is straightforward because the problem was introduced in one identifiable commit. Underlying both is the concept of hermetic builds, enforced by their internal build system, now open-sourced as Bazel. A hermetic build cannot reach the network during compilation. It cannot depend on ambient system state. Given the same source inputs and the same toolchain, it produces bit-for-bit identical outputs every single time, on every machine in the fleet. This makes the build system a trusted black box. If it passes on one runner, it passes on all runners. There's no works on my machine because the machine is irrelevant. Netflix operates a streaming platform serving over 100 million concurrent viewers at peak times, deployed across multiple cloud regions, on hardware ranging from modern browsers to 8-year-old smart TVs. At that scale, no test suite can simulate production. The failure modes that matter are emergent. They appear only under the specific combination of real traffic patterns, real devices, real geographic distribution, and real content catalog interactions that only production can generate. Netflix's response to this reality is to extend CI into production itself. Their pipeline doesn't end at a green test suite. It extends into a canary deployment phase where new code is shipped to a small fraction of real traffic, typically around 1%, and held there for a defined bake time that can range from 60 minutes to several hours depending on the risk profile of the change. During the bake time, automated systems watch a set of key metrics: error rates, latency at the 99th percentile, stream start failures, playback errors. These metrics are compared against a baseline measured from the stable fleet running the previous version. If any metric crosses its threshold, if error rates climb more than some small fraction of a percent, if P99 latency spikes, the pipeline triggers an automated rollback without any human intervention. This automated rollback is crucial. By the time an on-call engineer has seen an alert, woken up, logged in, and assessed the situation, a bad deploy can have degraded experience for hundreds of thousands of viewers. The automated gate at Canary Time catches problems in seconds and rolls back in under 2 minutes. Their tool Spinnaker, which they open-sourced in 2015, is the engine that powers this entire pipeline and has been adopted by hundreds of companies since. Shopify runs one of the largest active Ruby on Rails codebases in the world, a monorepo where hundreds of engineers commit daily to a single repository that handles checkout flows for millions of merchants. When your team is small, running every test on every commit is fine. When your team is large enough, it becomes physically impossible to keep CI under 10 minutes without being smarter about which tests you actually run. The approach Shopify pioneered at scale is called affected-only test runs. The fundamental insight is simple: if you change the payment processing module, the storefront rendering tests are almost certainly irrelevant to your change. Why run them? They're not going to catch a bug introduced in payment code. Running them wastes CI minutes and adds latency without adding safety. In practice, implementing affected-only runs requires two pieces: a dependency graph of your modules, who imports whom, and a diff of which files changed in the current commit. The CI system walks the dependency graph from the changed files outward and identifies every module that could transitively be affected by those changes. Only those modules tests run. Everything else is skipped. Shopify's engineering team reported in their public blog posts that this optimization reduced their median CI time from over 20 minutes to under 5 minutes for the typical single module commit. That's a fourfold speedup without touching a single test, without buying additional runners, without changing any testing strategy. Just being precise about which tests are actually relevant to each change. The technique has since spread widely, with tools like NX for JavaScript monorepos and Bazel's query language providing native support for this pattern. The fastest possible single machine test run is still bounded by one CPU, one thread of execution, one sequential flow. If your full test suite takes 38 minutes running serially on one machine, you can optimize the tests themselves, you can remove redundant coverage, you can swap out slow test doubles, but there's a hard ceiling to what single machine optimization can achieve. Parallelism breaks that ceiling entirely. The core idea of fan-out CI is straightforward: split your test suite across multiple runners that execute simultaneously, then collect all their results and treat the combined output as a single pass or failgate. If you have 38 minutes of tests and you split them across 8 runners, your wall clock time becomes approximately 5 minutes, the time of the longest shard regardless of how many total tests you have. The critical subtlety is how you split. Naive sharding splits by count: runner 1 gets tests 1 through 125, runner 2 gets 126 through 250, and so on. This almost always produces badly unbalanced shards because test execution time is not uniformly distributed. A single slow integration test might take 4 minutes, while 100 fast unit tests take 30 seconds combined. If that slow test lands in runner 7 takes 4 times longer than everyone else and becomes your pipeline's bottleneck. The right approach is to split by historical duration. Most modern test frameworks, PyTest for Python, respects format JSON output for Ruby, just shard flag for JavaScript, can record how long each test took in previous runs and use the data to generate shards that balance total execution time rather than test count. The result is shards that finish within seconds of each other, and a pipeline wall clock time that actually equals total test time divided by runner count. A CI pipeline is not a bag of checks that run in arbitrary order. It is a deliberately sequenced feedback ladder, ordered from cheapest to fail at the top to most expensive to fail at the bottom. The principle behind this ordering is simple: the moment any stage fails, every subsequent stage is cancelled. You want failures to surface at the cheapest possible point in the pipeline, because cheap failures save runner minutes, save developer time, and provide the fastest possible actionable signal. Lint runs first. In most projects, a linter like ESLint, Robocop, or Rough will catch syntax errors, obvious anti-patterns, and style violations in 8 to 15 seconds. If your linter catches a missing semicolon or a typo in a variable name, there's no reason to burn 2 minutes on unit tests before surfacing that error. Fail fast. The developer knows in 15 seconds that they have a trivial fix. Typecheck runs second if your language supports it. TypeScript's compiler, MYPY for Python, the Rust compiler's type system, these catch a large class of logic errors in 30 to 90 seconds without running any test infrastructure at all. Early, cheap, actionable. Unit tests run third. 2 to 4 minutes for most codebases. These catch business logic errors in isolated functions. No network, no database, no external dependencies. Pure, fast, deterministic. Integration tests run fourth. These test the contracts between your modules, database queries, API calls against mocked or containerized dependencies, service boundaries. 4 to 6 minutes. More expensive but much higher confidence. End-to-end tests run last, and critically, they should test only the most critical user journeys: login, checkout, the 5 things that would cause an immediate production incident if broken. Not every feature. Not every edge case. Those belong in staging. The full E2E suite in CI should clock in under 3 minutes and catch only catastrophic regressions. Most 45-minute CI pipelines are not slow because the tests are fundamentally slow. They are slow because of patterns that were baked in on day one, when the project was small and the pipeline ran in 4 minutes, and nobody ever went back to revisit them as the codebase grew. There are 3 anti-patterns that account for the majority of wasted CI time in first-generation pipelines, and they are present in the majority of engineering teams that have never deliberately audited their CI. The first is reinstalling dependencies from scratch on every run. When a Node.js project has 800 packages, a number that is frankly modest for a modern frontend, a cold npm install takes 90 seconds or more even on a fast network. Multiply that across 100 CI runs per day and you're burning 2.5 hours of runner time per day just downloading packages that haven't changed. The fix is a 15-line change to your workflow YAML. Use actions/cache to store the node_modules directory keyed by the hash of packagelock.json. If the lock file hasn't changed, the cache hits and installation takes under 3 seconds. The second is serial test execution when parallel execution is possible. 2,000 tests running on a single runner when a matrix strategy could split them across 8 runners in parallel. The implementation is maybe 20 lines of YAML. The speedup is 8-fold. This is the single highest leverage optimization available to most teams, and it requires 0 changes to application code. The third is rebuilding unchanged artifacts. Recompiling a Docker image from scratch because CI doesn't know which layers changed. Rebuilding a front-end bundle when only a back-end file changed. Content-addressed build caches, Docker build Slayer caching, Bazel's action cache, NX's computation caching solve this by storing build outputs keyed by their inputs. If the inputs haven't changed, the output is retrieved from cache instantly. No rebuild. No wasted minutes. A hermetic build is fully isolated from its environment. Given the same source inputs, it produces bit-for-bit identical outputs regardless of which machine it runs on, what time of day it is, what other processes are running, or what the ambient system state looks like. This is not a best practice to aspire to. In teams running CI at any serious scale, hermeticity is the foundation on which everything else rests. The reason hermeticity matters so profoundly is trust. When a build is not hermetic, you cannot reason cleanly about why it passes or fails. A test that passes on your laptop might fail on the CI runner not because your code is wrong, but because the runner has a different version of Python installed, a different system locale, a different set of environment variables, or because the test makes a network call that times out under high CI load. These failures are maddeningly difficult to debug because the bug isn't in your code at all, it's in the mismatch between your environment and the CI environment. Works on my machine is not a developer excuse. It is a CI failure. If the build is hermetic, works on my machine cannot be true. The build either works on every machine or it works on none, because the machine is excluded from the set of inputs that determine the output. Practical hermeticity means pinning all dependency versions, not just your direct dependencies but the entire lock file tree. It means never making network calls in unit tests. It means using fixed random seeds in any test that involves randomness. It means stripping timestamps from build artifacts. It means using containerized build environments where the exact OS, runtime version, and toolchain are specified and reproducible. Tools like Nix take this to its logical extreme. A Nix build is guaranteed reproducible down to the binary level. For most teams, disciplined use of lock files, setup actions, and Docker achieves 90% of the benefit at a fraction of the complexity. For decades, the canonical model for structuring a test suite was the test pyramid. Many unit tests at the base, cheap, fast, isolated. A smaller layer of integration tests in the middle. A thin cap of end-to-end tests at the top, expensive, slow, brittle, but covering the complete system. The pyramid's premise was that unit tests were the most reliable and the cheapest to run, so you should have the most of them. That premise held reasonably well for server-side application logic where the unit being tested was a pure function with predictable inputs and outputs. But it has been increasingly challenged for modern web applications where much of the interesting logic lives in the interaction between a user interface, an API, a database, and a set of business rules that span all three layers. Kent C. Dodds coined the test trophy model specifically to address this. In the trophy, integration tests form the wide middle, tests that spin up a real database, make real API calls within your own service, and verify that the pieces work together correctly. These tests give you much higher confidence per test than isolated unit tests of internal implementation details, because they test the thing that actually runs in production, the assembled system, not the individual parts. The practical implication for CI is not that one model is universally right. It's that you should measure which types of tests provide the most bug-catching value per minute of CI time in your specific codebase, and allocate your testing investment accordingly. Both models agree on one principle: end-to-end tests in CI should be a smokescreen covering critical user journeys, not a comprehensive regression suite. The comprehensive E2E suite belongs in staging, where it can run without the 10-minute constraint. Here is a thought experiment. Your application code goes through code review, has tests written for it, is lint, is type-checked, is deployed incrementally to staging before it reaches production. Your CI configuration, the YAML files in .github/workflows that control every single build, every merge gate, every deployment is often merged by a single developer in 30 seconds with the message fix CI and no review whatsoever. There is a deep category error embedded in this common practice. Your CI pipeline is infrastructure. It controls who can ship code and under what conditions. It gates every deployment to production. It shapes the daily workflow of every engineer on your team. When it breaks, it doesn't break one feature for some users, it breaks the entire team's ability to ship anything at all, potentially for hours. A bug in your application code is a production incident. A bug in your CI configuration can be a multi-day engineering paralysis event. The review rigor should reflect that. Concretely, this means requiring at least 2 reviewers for any change to workflow files. It means running your own CI linter. ActionLint is specifically designed to catch type errors and logical mistakes in GitHub Actions YAML on pull requests that touch .github/workflows. It means pinning every third-party action to a full commit SHA rather than a mutable version tag, because a tag like at v4 can be moved by the actions maintainer or an attacker who has compromised the maintainer's account to point to a completely different, potentially malicious version of the code. A full SHA cannot be moved. What you pinned is what runs, forever. Treat your CI configuration with the same respect you treat your application code. It deserves the same review, the same testing, and the same documentation. You cannot improve what you do not measure. This is a cliché because it is true, and it applies to CI pipelines with particular force. High-performing engineering organizations treat their CI pipeline exactly like a production service. They define SLOs, service-level objectives, for key health metrics, they maintain dashboards, and they have processes for when those SLOs are breached. Most engineering teams do none of this, and as a result they have no systematic way to detect CI degradation until it becomes a crisis. The most important CI health metric is pipeline duration percentiles, specifically P50 and P95. P50 is the median pipeline duration, the time at which half of your runs complete. P95 is the 95th percentile, the time at which 95% of your runs complete. The goal for P50 is under 8 minutes and for P95 under 15 minutes. The gap between P50 and P95 is a signal about your long-tail problem. If P50 is 6 minutes but P95 is 22 minutes, you have a specific set of slow or flaky runs that are disproportionately degrading experience for a significant fraction of your team. Flake rate is the second critical metric. the percentage of pipeline runs that contain at least one test failure that disappears on rerun. A flake rate above 1% means your team is spending meaningful time rerunning pipelines and losing trust in green results. A flake rate above 5% is a CI emergency. Queue depth measures how many pipeline runs are waiting to start because there aren't enough runners available. If your queue depth is consistently above 5 or 10, you're either undersized on runners or you're running too many unnecessary pipelines. Both are solvable but require different interventions. GitHub's built-in Actions Insights tab gives you basic duration charts. For production-grade observability with proper SLO tracking and alerting, teams export pipeline data to Datadog, Grafana, or purpose-built tools like BuildKite Analytics. Let's bring it all together with a realistic scenario. You've just joined a team. Their CI pipeline takes 45 minutes end-to-end. Developers are visibly ignoring failures, rerunning rather than investigating, merging PRs with yellow statuses, skipping the pipeline altogether for small changes. The three laws are all broken: it's slow, the results are sometimes flaky, and the gate is soft. Where do you start? The instinct for many developers is to rewrite the tests, to spend weeks refactoring slow tests into faster ones. This is often the wrong first move. Test rewrites are high-effort, high-risk changes that require deep familiarity with the codebase. They can take months to show meaningful results. The instinct for others is to change CI providers, to migrate from GitHub Actions to some other platform in the hope that the hardware is faster. This is almost always the wrong move. The platform is rarely the bottleneck. The workflow is the bottleneck. The right first fix, in the overwhelming majority of cases, is to add dependency caching and parallelize test execution into shards. These two changes are typically a day's work on the CI configuration. They require no changes to application code. Dependency caching alone can cut install time from 90 seconds to 3 seconds. Test parallelism across 8 shards can cut a 38-minute test run to 5 minutes. Combined, a 45-minute pipeline becomes a sub-10-minute pipeline before you've touched a single test. That's the insight this chapter has been building toward. Great CI is not primarily about the tests. It's about the pipeline architecture around the tests, the ordering, the caching, the parallelism, the gates. Get the architecture right and the tests become dramatically faster without changing a line.